Welcome to Quantum Tech Investments and Applications, the podcast. I'm your host, Bob Sutor. This is produced by Katie Sutor and brought to you by our company, Sutor Group, Intelligence and Advisory. This is episode 2025, 11:15. That is, we recorded it on November 15th, 2025. Today we have three topics. First is a brief update on the DARPA Quantum Benchmarking Initiative. We spoke at length during the first episode on that topic, and there's a little bit more to say about one company. This last week, I was in Atlanta, Georgia, in the United States, to attend the IBM Quantum Developers Conference. I'll have some of the news from that as well as comments. And then, mysteriously, I've got a topic labeled zeros and ones. You'll have to see what that's about. So first, the update on DARPA QBI. When the DARPA Quantum Benchmarking Initiative started in the Stage A, there were 17 companies, as we pointed out during the last episode. Two of those companies got absorbed by others, and so then there were 15. And then when DARPA announced they were moving to Stage B, there were only 11 companies. So 4 of them, for whatever reason, did not go from Stage A to Stage B. And we really didn't know why. I have heard that maybe there were some contractual problems. I can imagine maybe the companies didn't want to proceed. As far as I know, Rigetti Computing was the only one to make a statement, and they did so in their earnings announcement for the third quarter of 2025. And this is what they said. Rigetti remains engaged with the Defense Advanced Research Projects Agency, DARPA, on Stage A of the Quantum Benchmarking Initiative, QBI. On November 6, DARPA announced the companies initially selected to participate in Stage B of QBI. Although Rigetti was not initially selected for Stage B, the company received constructive input from DARPA regarding its proposal, and its dialogue with DARPA is ongoing. Rigetti is optimistic about being chosen for Stage B in the coming months. That's good to hear, and I wish them luck. It is a little confusing here, I might say. There seem to be some companies still in Stage A. As we see here, some may move to Stage B. I also understand that maybe other companies will someday enter into a Stage A and then their Stage B, and maybe some will move to a Stage C, and possibly one will come out the other end, basically saying that DARPA believes they will produce by 2033 a quantum computer that has all these advantages that we have been promised. So expect news on this topic to continue somewhat fragmented, because they'll talk about this company, this stage, and so forth, and things like that. Again, good for Rigetti. I hope they do well and can move to Stage B. Second topic is about IBM and their developers conference. Now, first, I have to give some disclosures about myself and IBM. I was an employee of IBM for 39 years, and the last 5, more or less, with IBM Quantum. And being there for so long, and being an executive, I was a vice president for many years, I have some stocks still in the company. And being there for so long, somebody turned at more than half of the computer age, I have some retirement benefits that I accrued by working there. Moreover, specifically for this conference in Atlanta, IBM paid for my airfare and the hotel travel expenses to the conference. Now, let me say this is not unusual. This is not really special for me. Companies, especially large companies, will often pay analysts or people who were analysts or pretend to be analysts or maybe just analyzers like me to attend their conference, meet with their executives, their technical people, hear the talks, get the news, all these sorts of things. So now you know it. Yeah, I have a lot of history with IBM, and things continue, as you can imagine. Now, I don't think in what I'm about to say, these things will seem slanted because of this relationship, but you should know this, and now you do. So the first thing is, it was in Atlanta, Georgia. This is the first time I've been in Atlanta, or at least out of the airport, in probably 20 years. There's just not a lot of technical conferences, or the ones I've attended, have been in Atlanta recently. It was nice to get out of the airport. I didn't have very much time there. It was really just one night. It's one of these trips where you land at the airport, you go to the hotel, you do everything in the hotel, you go back to the airport, and you go home. And that's what happened. Now, at this conference, among the many things that IBM announced, they highlighted 2 new quantum computing chips. One is called Nighthawk, and the other is called Loon. So let's look at those two chips and what IBM is trying to do with them. So the first is Nighthawk. It's 120 qubits linked together with 218 next generation tunable couplers. What does that mean? 120 qubits. A qubit holds the basic quantum information. When we talk about superposition and things like that, that's the information that's held in a qubit. Nighthawk has 120 of them. Now, individual qubits aren't really that interesting when it comes to quantum computing. It's the 2-qubit operations, the things you can do with 2 or sometimes even more, 3 qubits at the same time. And when you do those, sometimes you can get entanglement. So you have to have connections between the qubits to do some of these interesting operations. And these are related to the couplers. Being tunable means that they can adjust exactly how they work for particular pairs of qubits. And also they can adjust them slightly to decrease the number of errors that they might have. This is the successor to Heron, and Nighthawk is due by the end of 2025. Now, 120 qubits, if you're keeping track, that's actually somewhat smaller than Heron. All right, maybe we'll see some future version of Nighthawk or another chip with another bird name that has more qubits, but do not worry now about the number of qubits. I've said many times that we will make little quantum computers from, we will make big quantum computers from little quantum computers. So think of this as a little one. In IBM's case, what they'll do is they will link them together via microwave connections and be able to communicate quantum information between them. Maybe someday they'll get so big they need optical connections to do this, but that's what we're talking about. So think of this as being modular, and one of these chips as being one of the modules that we connect these. Now, I want to talk about a particular phrase, and especially one word that comes up in a lot of these discussions. And I was confused occasionally when I heard this. And so I want to make it clear. I also saw one article which was completely wrong regarding this topic. So the phrase is 30% more complexity. If you just take a generic view of saying something's complex, oh, that's really complicated. Why'd you make it so complicated? The full phrase here that I took that from is allow users to accurately execute circuits with 30% more complexity. So the complexity refers to the circuits. That is, they're more sophisticated. The circuits are what implement the quantum applications, right? And so quantum software engineers, they write them, some software processes them. Eventually, these modified circuits run on the actual chips in IBM's case. And what they're saying is that they can be much more sophisticated circuits than they were before. So in this case, the complexity is a good thing, what they mean here. Now, the architecture is also more complex, you would expect. As everybody introduces better and newer chips, they get more complex. But we can do that. And particularly if you're using very modern methods, which we'll see in a moment, you can take that into account. So architectures improve, they become denser, they become more sophisticated, and yes, even more complex. But when we see this in the context of IBM, the term complexity, good thing, not bad thing. Now, the other chip is called Loon. And all of IBM's chips have bird names. It's something they started a long time ago, even when I was there. They're very creative about this. I actually don't know what the process is anymore to determine what bird or that bird in the past. I mentioned heron, they've had eagles and things like that. Loon is an experimental processor. That means it's done on the side. Whereas Nighthawk, think of it as mainstream. Loon is where they're going to try new things. And it's a new architecture specifically for error correction and the new error correcting codes that people are developing. Now, it also has better connectivity. So these chips have a square connectivity architecture. So just think of vertical lines and horizontal lines with a little space between them, and where they intersect, that's where you stick a qubit. So it's a square architecture. This is different from the previous heavy hexagon architecture they had, where you can imagine a 6-sided figure. You put a qubit on each of the corners, and then you put one in the middle. So they've simplified, they've just gone to a square. Other people have done that in the past. I kind of figured they'd do that eventually. Now, if you imagine this, so think of the grid I described. You've got one qubit, right? You have one above it or north of it, one below it, south of it, and then one to the left and the right, to the west and the east, and things like that. If I want one qubit to have an operation with another qubit that's further away from that, I have to play telephone. So I have to exchange quantum information from one qubit to the one next to it, to the one next to it, and so forth. And we use what are called swap operations to do that. Like the game of telephone, the message, the information can get distorted somewhat. So this is a chance to add extra errors the more of these you have to do. It also adds more operations, which cuts down on the amount of time that you have to do what you might consider really useful things, as opposed to just swapping like this. So Loan is going to be able to have qubits talk to other qubits that are not just the nearest neighbors, a little bit further away from that. It makes the connectivity or the topology that much more interesting. It allows the compiler, when it's laying out what sorts of things should run where on the chip, it gives it more options, and it allows other chance to optimize what's going on here. Now, here I want to point out this is primarily an audio podcast, but it's also a video podcast. If you happen to be watching it on Spotify or watching it on YouTube, there are a few graphics, there are a few words. I will read through or talk about anything that's essential. On this particular slide, I have a photo supplied by IBM of the Loon chip with its 112 qubits. It's really just a shiny gray rectangle. And this shows that they really made one, I guess. I can't see what's inside of it. At the conference, they did show some of what the internal architecture looked like, but there it is. And they very proudly brought out one of these and a Nighthawk as well, saying, look at this. Other vendors do that as well. It's show me your chips, and the people walk out and they do this. Now, again, if you're also looking for this, if you'd like to read more about the IBM press release, there's a QR code on this slide, as there are others. But seriously, if you just want to do a web search on IBM, Nighthawk, and Loon, you will find it, and you'll find some other articles as well. So video if you got it, but you're not missing anything if you're just listening to it as well. Now, these chips, with their added complexity, are now being fabricated at the Nanotechnology Center in Albany, New York. So this is related to the State University of New York at Albany. Also, Albany is the capital of New York State in the United States. It's about a 2.5 hour drive north of New York City. It's definitely upstate. And in fact, upstate New York has an awful lot going on for it and in it about quantum. We have Albany, we have the Air Force Research Lab in Rome, New York. Corning is in upstate New York. Photonics-wise, both Albany and Rochester, New York, are very strong. So there's much, much more to New York than just around New York City. So IBM is moving to 300 millimeter facilities, and they showed a wafer that has lots of little Nighthawk chips. Now, these wafers, they're circular. And if you hold them just right in the light, you see all the colors of the rainbow, and they're very pretty. There's a photo here, and again, you can find it. So what does this allow IBM to do? It allows them to use state-of-the-art fabrication facilities instead of just what they have at IBM Research. It's a much faster process. They can design and get chips to test in much shorter time. They have a 10x complexity advantage. Again, complexity in a good way. The chips can have that much better, more sophisticated architecture. And also, this allows them to both design and test multiple architectures at the same time, much faster. So they have an idea, they can try it out, they can get a chip, they can see if it works, and they can go back to the drawing board and modify it, and so forth. So this is going to accelerate how fast they can do this to get to the chips that they need by presumably 2029 or maybe a little bit longer, that will have the type of quantum advantage that they've been talking about for practical sorts of things, and certainly to give us eventual fault tolerance through error correction. Now, I want to turn to software a little bit too. And so there was all this hardware, but what about the sorts of problems that you try to do with quantum computers here? Sarah Sheldon from IBM, she's a senior technical manager, PhD in IBM research. I've known her for many years. She and I made up the caffeine example you may have seen in my book or elsewhere. And we did this moments before we were going to talk to the IBM board of directors to give them the first introduction to the new program that eventually became known as IBM Quantum. So she and I go back several years on this, and she focuses a lot on algorithms and applications and things like this. So she highlighted four specific areas. One is Hamiltonian simulation. A Hamiltonian describes the energy in the system. What the heck does that mean? You need a lot of math, you need a bunch of physics to understand it, but it's essentially something that quantum computers understand. You can map the problems to qubits, you can initialize it, you run it, and you can optimize it, and you hope you'll get the right answer. It's a very geeky, let me say, physics type of thing. And for the applications that you might have, such as chemistry, or even in some cases, financial services, you have to map them to these Hamiltonians. And the simulation simply says you're simulating some sort of physical process, but in a quantum computer. And that might be chemistry, as an example. Optimization is another topic. Machine learning is another topic, and differential equations. So machine learning, people have talked about for a long time. There are some issues. We'll return in a moment to that. Optimization fell out of favor for a little while with quantum computing because it seemed like we really just couldn't use the quantum computers long enough to get good enough answers of size. With some newer methods, they highlighted that optimization is very much back in the frame for doing things with quantum computers. Now, the new topic, if you will, is differential equations. Now, it's actually not new, and differential equations have been around basically as long as calculus has been around. And differential equations are used to describe many processes that are changing. If you ever take calculus or multivariable calculus, you start seeing differential equations. They may not be called that initially, but those are what are used to model weather, for example, and different things like this. And when you have multiple variables, they get very sophisticated. People had postulated that this would be useful, but I think the quantum computers themselves weren't good enough to really consider this a practical application. That's changing. And to me, of all of them, this is the most exciting area. It's very mathematical, but if you are in engineering, if you are in physics, if you are in some types of chemistry and things like this, doing aerospace calculations and things like this, it's differential equations. And if they make great progress here in differential equations, this is going to be really significant as an area. So I want to highlight optimization has risen up again in differential equations, where the math is somewhat related to what's going on anyway, but as a topic is now really in the forefront here. Now, the second point I want to mention that Sarah talked about were two parallel paths to getting advantage. That is, when quantum computers combined with classical computers are significantly better in some way than just classical systems alone. So the first is, and I'll read them, empirical tests of quantum usefulness, not utility, usefulness. I don't really like the word utility. And then the second is scientifically rigorous proofs of advantage. Now, the word empirical here is really important. And on the slide, I have a definition, but what it means, according to the Cambridge Dictionary, is that it's based on what is experienced or seen rather than on theory. So let me cut to the point on this. What this means is if you're using somebody's quantum computer and you are getting pretty good results and you are happy with them, more power to you. We're not going to prove theorems or anything like this. If it's heuristics, if somehow you're seeing an improvement, that's great. Do it. We don't have the purity associated with this. But on the other hand, yeah, people do focus on whether there is a theoretical, a provable advantage to certain algorithms compared to classical. Now, heuristics often enter into these empirical tests. We're going to try something special. We're going to take some shortcuts and hey, it works. Great. So don't get so hung up, IBM is telling us, on these notions. of pure definition of practical quantum advantage. If it's good for you, great, go for it. And I like this is a relaxation a little bit. I got to tell you, I'm a mathematician. I tend to like the rigorous proofs here, but we're talking technology. We're talking about getting solutions to problems people care about. However you do it, whether it's quantum, whether it's classical, whether it's AI, whether they're all together, go for it. Okay, that's really what they were trying to say. There was one main day of presentations, of discussions, and then 2 days that were challenge hackathon oriented. I did not stay for those. Now, in what follows, our third topic here, I just want to point out, I wrote a book, Dancing with Qubits. It's in the second edition. Here, I like to say it's the sponsor of our podcast here, but I pointed out because it does discuss most things you need to learn to do quantum computing from a mathematical perspective, and it starts in very basic ways of doing this. I will occasionally pull out some topics from this and talk about it on the podcast. So I want to say it's here because on the next slide, which is finally our zeros and ones, I want to highlight some things. When we use a quantum computer, typically we don't start with things actually in the quantum computer that are like numbers and texts and videos and things like this. Classical computers, at least the information is stored in digital form, are whole bunches of zeros and ones, right? Every character, like an A or a capital T or something like this, it's represented by zeros and ones, and you use a certain number of these. If you're talking about machine learning, you have a lot of data, right? And if it's digitized, it's all zeros and ones and things like this. That is not the natural format that quantum computers use. We use superposition, we use multiple qubits, and so somehow we have to convert the classical information into a quantum form, and then we can run quantum algorithms for this. And this is called encoding data, so encoding classical information into qubits in some way. Quantum step preparation means that we are preparing the classical data and doing things to it. So we are representing that information in quantum states of typically many qubits. So that's what quantum state preparation means like this. There was a blog entry that I just saw from about Penny Lane from Xanadu, and it was a brief, really nice article called How Quantum State Preparation Can Make or Break Your Hackathon Project. And so the point here is saying, hey, I got this great idea. I'm really smart. I came up with a quantum algorithm or a modification, more likely, to do something. And oh, this is so great. If you choose the wrong way of putting your classical information in the quantum computer, your algorithm may not work, may not be appropriate, or you just can't do it, right? A problem with a lot of the hyped examples of quantum computers is they talk about the stage 2. Look at my amazing quantum computing algorithm, and this and stunning, and this and that, and does everything. Unfortunately, step 1 is taking the data and manipulating it and encoding it to use in a quantum computer. Now, in some cases, the general case, this can be an exponential process. It means that as you get more and more data, the problem gets harder and really hard. Exponential improvement is great, but an exponential problem or a process gets super, super slow. So whenever you hear about these really hyped applications, many times they're for really small problems because they can't do bigger problems. It just zooms out and gets so bad. So if you don't prepare your data in the right place, it won't be useful. There are always research articles that are talking about this. It comes up a lot with quantum machine learning. A couple of people on LinkedIn posted comments to a remark I made for articles on Arxiv, ARXIV. The first is called How Many Qubits Does a Machine Learning Problem Require? And Sonika Jory sent that to me. And then another one, EHANS, Quantum Protocol for Polynomial Computation on Real Valued Encoding States. That sounds geeky. Basically, what they're saying is, how do you take real numbers with decimal points and things like this, and how do you actually get those efficiently into a quantum computer to do something with this? And that was sent to me by Talita Persiano. And I apologize if I did not pronounce your name correctly. So there's a lot of work. But here's the caution. If you ever read an article that says something like, we are producing petabytes of information every single day, and thank goodness we have quantum computers that can process all this in the blink of an eye, stop reading. We can't even get that information into a quantum computer. And if they're making that fundamental mistake, there's probably a lot more in the article. So just quit, get on with your life, go read something else. It's a fascinating topic on how to do it. It combines math, it combines computer science, and so forth. And it's essential. It's step one. Get the data into the computer, then doing something with it. All right, so let's finish up here. Is the podcast that is related to our Substack. Recently, we talked about the Rigetti financial results. I mentioned those much earlier when we were talking about QBI. I mentioned the debrief, I mentioned we had an earnings brief, D-Wave, INQ as well. I put reports on there for paid subscribers and things like this. And of course, we will list the podcast and what we're doing. This podcast is available for sponsorship for companies, for organizations, and for conferences. You can grab some time. You can sponsor episodes, several episodes. Contact Katie at Katie Sutor, KATIESUTOR @sutor.com for details. And then finally, there's legal stuff associated with this. If you go to sutor.com, you can find the, as I term it, legal stuff. Formally, it's the copyright, notices, disclosures, disclaimers, and licenses page on the Sutor Group website. Thank you very much for joining, and see you next time. Take care.